All right, welcome to General Relativity and Geometric Algebra 1. We're going to be talking about tetrads. When working in curved manifolds, there are objects called tangent spaces. And so if M is the manifold, then what's called the tangent manifold is Tx. So Txm is the tangent space at point x. Or rather, instead of point, we say at coor. So I'll just erase that. At coordinate x. The coordinate basis, so that is the basis for the tangent space at this coordinate x. So the coordinate basis for Txm is this set right here, G mu. And we're going to talk about what these are exactly. So it's written G mu. It's called the coordinate basis. So the tangent space, and then this is called the coordinate basis. Do a better underline here. So we have the coordinate basis, where G mu is defined as the derivative in the muth direction of the coordinate x. And you can think of this coordinate x as being just the vector x in the space-time algebra, and then you take the derivative in the mu direction, and you get G mu. And lastly, it satisfies a metric that is G mu dotted with G nu is equal to G mu nu, where G mu nu is the coordinate metric. Coordinate metric. In general, G mu is non-orthonormal. So in general, G mu, or the set rather, the basis, G mu is non-orthonormal. We can, however, create an orthonormal frame at this coordinate x. So we can create an orthonormal frame. Come on, let me erase this. An orthonormal frame, or rather, I'll say basis. We can create an orthonormal basis at point or at coordinate x, and then from the coordinate basis. And this is called the tetrad. And it is written as gamma m. The tetrad satisfies the Minkowski metric. Gamma n, m and n is equal to eta m n, which is going to just be 1, 0, -1, and then I don't want to write all of that down, so I'm going to just copy it from up here. Therefore, this basis, the tetrad, so therefore, the tetrad functions as a basis for or for an STA for a spacetime algebra at the coordinate x. Because we're working with a GA, we call or we relabel the tangent space we relabel the tangent space as the geometric tangent space. So when you're working with the tangent space, but you're promoting it to a geometric algebra, then it's the geometric tangent space at coordinate x for the manifold M. Okay. The tetrad and the tetrad gamma M and the coordinate basis G mu are related by what's called a Vierbein. Are related by the Vierbein. Vierbein. I probably should look up how to pronounce it. I cannot get a good underline here. There we go. By the Vierbein E M mu. And this is just a number that is indexed from M, the tetrad basis number or index, and then the mu, the manifold index or the coordinate index. And how exactly does this work? Well, we have the following. For G mu, we have E M mu and then gamma M. Now for the reciprocal basis, we have G mu equals E to the M and then mu and then gamma M, like this. And there are some neat little properties that are satisfied by this, namely that E M mu E E nu M is going to just give you the Kronecker delta of mu nu, and then E to the M mu E mu N is also just going to be the Kronecker delta. So there are these properties here, which are implicitly defined here. And this finally implies that the coordinate metric can be rewritten as E mu E n nu. This m is way up there. Eta m n. So you have these transforms which bring the local tangent Minkowski space or Minkowski metric. So the tangent Minkowski metric, these will bring it to the coordinate metric. And lastly, the line segment, or specifically the differential line segment, is going to be ds squared equal to g mu nu x mu x nu, and this is going to be eta mn. We can then substitute in the verbine, and we still have x mu dx nu, but then we can, first of all, just make this go in the middle. Then we can sum over these indices, or mu mu nu nu, and we get eta mn partial x m, or and then dxn, not partial. So we get this. So you can see how you can, when you're looking at a line segment in a general line segment, and you're looking at it in the coordinate of the GA, then you can actually just turn it into looking at the line segments in the, or in the, what do you call it? The tetrad frame, or the tetrad basis. So how does this look geometrically? Well, this is what it looks like. So the curves here, this is the manifold. And then the coordinates are just points here. So these are different coordinates. If we look at the coordinate basis, recall that the coordinate basis is defined as the derivative in the mu direction of x. So if we look at the derivative of this here, then we end up getting this and this direction here. And likewise, we get the pink for all the others. So the pink give you the coordinate basis vectors. And then when you move into a tetrad, you get these orthonormal frames here. And so if I were to look at like a little curved segment here, then the curved segment, that's what this ds is. It's like it's a small differential line segment. And then it can be expressed in terms of these pink vectors or in terms of these red vectors. And these are the essentials of tetrads and how we can use them to work with geometric algebra even when we're doing general relativity.